So here we start off by seeing the magnetic field on the outside.
Okay.
I've already done that.
Right.
B equals mu naught I by 2 pi whole into 1 by r.
Right.
And again integral B dl equals mu naught I. Here we consider a path which is outside, a circular path.
Okay.
And the distance of the path from the center of the wire will be r.
Right.
This is actually not I. I is the current carried by the whole wire.
Right.
So we see a V into 2 pi r equals mu naught I because the whole current will be carried inside by the wire. So
Okay.
for outside it's always I. We don't need to find, like, divide it into area and find how much that area is covering.
Right.
So B equals mu naught by 2 pi whole into 1 by r.
Okay.
And if we see it on the graph, it basically comes out to be like this. After r, this is the magnitude of the magnetic field because it is 1 by r,
Right.
so it flows down.
So what about the field before this, inside R?
Yeah, inside r, let's see. Inside r, it was like this because it was
Okay.
directly proportional to r.
Right.
So, and at this point, they both have the same, which is at the point where r equals a.
Right.
They have the same.
Alright.
So this is the graph basically of mod B with the radius.
Right.
Okay, so that we'll consider Amperes law. Yeah, in Amperes law, basically we find till now we have found out the magnetic field, the direction and the magnitude of the magnetic field associated with a particular current carrying element.
Right.
Now we'll find the force exerted by a magnetic field on a current carrying element.
Okay.
So let's see. Let's see the formula first. df vector equals I into dl vector cross b vector.
Okay. So could you just give me a brief background about Amperes law? Like, what are we looking at here? Like, what are we trying to find out?
Ampere law, let's consider it by an example.
Okay.
Say we have a magnetic field existing in space, b vector,
Right.
and we have a current carrying element through this. Let's say a wire is
Okay.
carrying a current.
So we are placing a wire in a magnetic field.
Yeah, we are placing a wire in a magnetic field,
Okay.
and it carries a current I, and we need to find, like,
So we are trying to find out the interaction between the wire and that's carrying the current and the magnetic field.
yeah, we find out the force of interaction
Okay.
that basically happens between the magnetic field and the wire. Basically, the effect of the magnetic field on the wire
Oh,
in
acha.
terms of
Okay.
the force.
Fine.
So let's see. Like, this is the magnetic field.
Right.
It's considered throughout the space, and we have a wire here oriented. This is P, this is Q, and the magnetic field is throughout, like here
Right.
for this particular wire. So dl vector, dl vector is the particular vector. This dl. Let's say we have to find out the force on PQ. So we travel from P to Q, and in that process we have a small vector, or dl vector, whose magnitude is dl, and the direction is the tangent to the orientation of the wire, basically tangent to the wire.
Right.
And the force on this is given by dl vector cross b vector.
Okay.
So, like, if there is a general case, we have to integrate it for every element. Like, if the field varies for every dl, like for here the magnetic field is different, and for here
Right.
this dl vector is different, then we have to integrate it.
Right.
But let's say we have a general case in which the b vector is constant.
Okay.
So for constant B vector, we find df equals integral I dl vector cross B vector. So since this is constant, I dl vector cross B vector.
Alright.
Considering I also constant, which is actually in most of the cases,
Okay.
because we are considering a wire and the
Right,
current
right.
flows and only a particular current will flow. So I integral dl vector cross B vector.
Okay.
So it's important to see what this integral dl vector comes out to be.
Okay.
Here we were considering the force on the wire PQ, which was kept in a constant magnetic field,
Right.
and the dl was the element which we encountered in the direction of the wire
Right.
and the magnitude dl. So if we add all these dl vectors,
Okay.
let's just see, let's say a point q is here randomly. So this dl vector plus dl vector plus dl vector. So by vector addition we see that p and q, if we integrate all the dl vector, it will come out to be this vector.
Okay.
Fine. Let's consider this point to be q dash.
Okay.
Okay, because that was q. So if we do it from p to q,
Right.
so it will come out to be this vector, which we can denote by capital L vector, which is the vector joining p to q
Right.
and the direction in the, from p to q.
Okay.
So for this we can, like for the wire PQ, if the magnetic field is constant,
Right.
B vector, we can directly write down the force as I into L vector cross B vector.
Okay.
And we have to, since we are also can tell the direction,
Right.
so say this is the L vector and the magnetic field was here, say it was also in the plane. So by doing the cross product L cross B, it will come out perpendicular to the plane of the paper.
Right.
But this thing has to be kept in mind that we can apply this integral dl vector only when the B is constant.
Okay.
Or let's say that there is a wire. This is P, this is Q. Current is also constant, flowing with I. But and it is kept, let's say it's kept in the xy plane,
Okay.
and say magnetic field is given as b naught x I cap. So in this case we cannot just like write down the whole wire for the whole wire
Okay.
as I into L vector cross B vector,
Right.
because while we derived this formula we considered B to be constant, but here B is not constant, it's a function of x.
Okay.
So in this case we have to, like if we can, in this case would be too complex because we don't know the actual curve.
Right.
But if we know the curve, then we can actually integrate for x, like b as a function of x,
Okay.
dot vector dot dl vector integral b into I. So
Right.
this will give the force in
Okay.
that case.
So now that we have looked at the Amperes law, we will move on to the one of the applications of Amperes law, which is basically looking at the force between two infinite current carrying parallel wires. So can you explain what this is about?
Yeah, force between two infinite parallel current carrying wires. So let's say we have a wire here, and these two wires are in the plane. These extend till infinite length. This carries a current I1,
Right.
and this carries a current I2.
Okay.
So mu naught I1 by 2 pi d. Now see, we have looked at this formula before, when we saw the current of a wire at
Okay.
a distance greater than r. So the distance is d.
Right.
Because the radius of a wire can be neglected as compared to the distance, it would be too small. So the exact current would be mu naught I1 by 2 pi d.
Okay.
This is the magnetic field which is produced by this wire at a distance d.
Okay.
Okay. So if we consider a particular section of this, say of length L, and we find the force on that, so we'll get L into I2. We are just multiplying here why so? Because the force was the force will be in this direction because the magnetic field is perpendicular to this
Right.
by the right hand rule. So and the I is here, I into L cross B. It will they all are at 90 degrees.
Right.
So it will give us L into I2,
So
which gives the force.
mu naught I1 by 2 pi d is the magnetic field at the distance d,
Yeah.
and then we look at the length of the wire multiplied by the current being carried in the wire, and that gives us a force, right?
Yeah. And because these these wires are carrying the current in the same direction, so the force will be attractive, and
Okay.
that can be found out by using the right vector signs or by the right hand rule itself.
Right.
So basically we find F by L because this length of the whole wire is infinite.
Okay.
So the interaction force would be infinite. But for a particular length L, we can find the force per unit length
Okay.
between the two wires, which will give us the interaction force. This is equal to mu naught I1 I2 by 2 pi d.
Okay.
This is basically the force between the wires.
So what's the concept of force per unit length over here? Like when we like taking the
Yeah, if we are asked force per unit length comes in because if we consider the whole second wire,
okay.
this L would be infinite. Okay, so like we'll get infinite force between two wires if they are kept.
Okay.
But practically that is not the case. Practically we can find only we can consider a particular section of the wire which we might be using
Right.
for any purpose, and we might be needing to find the force on that section. So we have a general formula for force per unit length. If we want to find a particular force on a particular length of wire, we can just
Right.
multiply it by L and get the force on that segment of the wire.
Okay.
If they are kept in the same plane and parallel and at a distance d.
Alright.
And this force will be attractive.
Okay.
Attractive if the current is in same direction. Else if the current is in opposite direction, then it will be repulsive.
Okay. And so we look at one of the applications of Amperes law, which is finding out the force between two infinite parallel current carrying wires. So we get the formula wherein the force per unit length between the
Between the two parallel
wires is given by the formula mu naught I1 I2 by 2 pi d, and this force is attractive if the current being carried by both the wires is in the same direction. Otherwise, if they are in the opposite direction, the force that will be existing between them is repulsive.
Yeah.
So now we'll be looking at the concept of magnetic movement, and we'll start off with the magnetic movement of a current carrying loop.
Let's say we have a loop here,
Alright.
and let's say this is in the xy plane and it carries a current I,
Okay.
and this is the M magnetic moment vector, and we define it by I into area whole into n cap, where n cap is the unit vector in the direction of z axis if this is in the xy plane. Or again we can find it by the right hand rule by curl of fingers around the loop in the direction of the current, and the thumb will give the direction of M, which is the magnetic moment. And if suppose there are a lot of loops or a coil basically like this, so and the current is going on anti-parallel. So the magnetic moment for this will be N, which is the number of coils, number of turns in the coil into area of a particular coil or the loop into I, which is the current, N cap, which gives the direction basically.
So before we move on, like, can you explain us what is the concept of the whole magnetic moment here?
We'll be needing this concept of magnetic moment to get the particular torque or the potential energy of a loop kept in a magnetic field or a solenoid consisting of coils.
So we'll look at this further into the chapter.
Yeah.
Right.
Now let's see the torque on a coil or a magnetic loop kept inside a magnetic field.
Right.
So the torque, the definition of the torque is given by torque vector equals m vector cross b vector.
Okay.
So this is basically the magnetic moment. Cross of the b vector, this is the magnetic field. Let's just see it by an example.
Right.
This is the xy plane, and current I is flowing. Let's say a magnetic field of B exists along the x-axis, magnetic field of B naught.
Okay.
So the magnetic moment will be, its radius is A, n is 1, area is pi r square I into k cap. B vector is B naught I cap.
Okay.
So the torque acting will be M cross B equals pi r square I B naught. K cross I will give J cap. So J cap means that basically the torque is along this. So what happens is that the force, the magnetic moment is there and the torque is acting. So basically force might also be acting. They will try to turn it in the direction of, this is Y, this is Z. It will turn the loop in the direction of YZ plane. That is what the torque does basically.
Okay.
So the torque will be like that. It will be oriented in the J cap, positive Y direction, and it will try to turn this loop.
Right.
Now we see the concept of potential energy. Of carrying loop or coil, but the condition is that basically potential energy is derived or can be derived only for those forces which are conservative.
Okay.
And magnetic force is not one of them. But
so how is this applicable here?
Yeah, so it is applicable only in the case in which the B vector, the magnetic field vector, is constant.
Okay. So it means like in a changing flux,
if the magnetic field is basically changing or it is not constant with respect to time or with respect to location, then we cannot apply this concept.
Okay.
Because that would not be valid, because in that case the magnetic field won't come out to be conservative.
Right.
But in the case in which it is constant, in that case it comes out to be conservative.
Okay.
But in general we say that it cannot be defined, because for like any case other than this in which it is not constant, it does not hold.
Okay, right.
So let's see for this. The potential energy is minus of m vector dot b vector. M is the magnetic moment and b is the magnetic field.